Alright, so I graded quiz 1 and homework number 1. So I have a few comments. So I uploaded the model answer. I'm not sure if you guys did you see the model answer? Okay, so one of the common problems that one of the problems was truss and the one was frame. I understand that many of you didn't know that the other one is truss. Maybe they were confused. But usually these systems, if you have something like this, and I'm making something like that, that's usually like a truss. We don't build the frames like this. But even if you work this as a frame, I assume that was frame, and I followed the answer with you if you did it right. So that's one of the things, like if you assume this as a frame in the quiz and moved on with because maybe, I don't know, like if I could have guided you and told you that this is a truss and this is frame, but I thought that you might know it on your own. But if you solved this problem as a frame, you will get the full point if you did it right. But most of you who did it as a frame, they didn't do it like the whole thing right, okay? All right, some of you consider this as truss, and who consider this as a truss consider this as a joint, like these two members are connected together. So if you did this, I followed the answer with you if you did it right or wrong. Some of you didn't consider that there's a joint here, and that's also fine. I see also some problems that you guys have, like for example, if I have a frame, like the frame that I give it to you, I don't remember actually how it was something like this, and here is fixed, and I did something like this. When I do something like this is not intermediate hinge, this is a hinge. Like hinge can be represented as something like this, or something like this. That's a pin, okay? So either this or this are the same thing, okay? So this allows moment. So the moment here is 0 and the moment here is 0, and there's two reaction, okay? So there is no moment here, right? That's also one of the things that I saw. And also you guys, some of you had a problem. There was like an intermediate hinge here, and that's, I believe it was something like a roller or something, or guided. Guided support, right?
Was like that.
Was like this?
Mm-hmm.
Are you guys sure? I think there was a guide here. Was it like this? Oh, okay. All right, so if you have intermediate hinge here, do you guys remember what is the number of conditional equation that this can give to you? It's only one equation because it connects two structures. Some of you dealt with it as it was something like this, this, and this. Like all of them are connected to this one. It's not right. If it's the case, S is gonna be equal to 2. But the case is that's connected to structure. It's not about how many members, it's about how it's look like. So that's in real life, that's how we model it as a structure analysis. But in real life, it's like this is a frame, something like this, like as a concrete member. And this is something like this. So all this as a connection has a moment, okay? And you have maybe something like, let's say, and then you have something like this on this frame, and you have another beam resting on this, and connected here and connected here, all right? Okay, so that's how the connection look like. So this beam is resting on the other frame, like something like this. So this beam can move, but this is a one frame, one piece, okay? So it's something like this. So that's how we model it as a structure analysis. So this is the model, this is the real example. So you need to be careful about this. And there was a rotational spring here, so it's not gonna make any difference. Just add one unknown to the problem. So this is actually mostly the comments, because we have quiz next Tuesday, and there will be problems like this. So be careful, because if you count the S wrong, everything's gonna be wrong, okay? If you count, and also the number of reactions. I don't know why you guys have problems with the number of reactions, like see all the end conditions. Here's 3, here's 2, 5, and here's 1. So I'll have only 6 reactions, okay? So what's the problem like this? Mm-hmm. Right? So if it's like this, so gives you 3 reactions, 2 reactions, so it makes it 5, and 1 reaction make it 6, okay? All right, so just count well, understand the problem, and definitely check if the structure is unstable or not, okay? All right, so, and I might ask you if it's externally or internally indeterminate, so you need to know how it's external or internally indeterminate. And that's also one of the things, because that's very important. So if I ask you to show the redundance and show the degrees of freedom, because most of you missed this part, you have to draw the structure 2 times. Like one time, for example, this is structure. I'm gonna draw it something like this, right? And I'm gonna have this, and you write here redundance. Okay? And you draw it one more time. Like this. And you have roller here, and you draw here degree of freedoms. That's what I want to see as an answer for the question. And then you start to list the redundance and list the degrees of freedom. So for the redundance, okay, let's put the rotational spring. For the redundance, what I want you to show me this structure as a statically determinant and show what forces that are not needed to make this structure stable. Like for example, I have a roller here, okay? What I can do, I can, for example, remove this, and this one is gonna be stable. If there is no spring here, it's gonna be unstable. But because there is a spring here, so it can restrain the moment, so this is gonna be stable. Okay, that's one thing that I did. I have a roller here, I might convert this to a hinge. And I make this as a hinge like this. This is still not enough. Yes, you made the structure determinant stable, but you have to show me what redundance, like what is the forces that you remove. So the forces that I removed, here there was a hinge, so that's redundant number 1, reaction number 1, and that's reaction number 2, and there was a fixation here, so there was a moment, that's reaction number 3. So that's the 3 forces that this structure doesn't need to be stable and determinant. So that's what I'm asking for. You draw the structure and see what end condition that this structure doesn't need. By the way, there is infinite numbers of solutions. Well, there's not infinite, but there is a number of solutions for this problem. Like I can make, for example, the easiest way to do this, I would remove this and I would remove this. This structure is determinant and stable, and here is the 2 forces, and here there is a 1 force. By the way, this roller is facing this way, so the reaction this way. So this one can work as well, and you write R1, R2, R3. If there is a fixed in your problem, try to make this fixed is the main thing that supports your whole structure. Like I can have this problem, maybe something, I don't know, like this, and there is a fixed here, and another one like here, and there is roller, and another one here, and there is hinge, and maybe something here as a hinge, so I can make it very, very big. But maybe the easiest way to do it is just to make one fixed, hold your whole problem, and all this is not needed. And all this is a redundant. Things that's not needed for your structure to be stable, because it's all based on this. It's like a tree, and the tree is fixed in the ground and has lots of branches. Okay, so the tree only needs the fixation coming from the ground to be stable. You don't have to hold the tree by your hand from here and your hand from here. You can remove all of this, okay? All right, so that's how I think about, like, if I'm solving a problem, I look at a fixation, like maybe I give you a grid. If I give you a grid, it's gonna be maybe something like this, and I'm gonna give you a fixed, and maybe hinged, fixed, all this. So if I give you something like this, all what I want is, I need this fixed and all of this I don't need. So all these are redundant. Once you remove a fixation, you put 3 forces. So that's a 3 redundance. 3, and I move the hinge, so 2, and 3, and 3, and start counting. Okay, I'm done with the external unknowns. I need to open this vent to make it stable. I mean, like, to make it like determinate. Right? So right now I have a determinate structure, stable, and have 3 reactions here. But you need to count all the redundants that you remove. Once you remove something, you put the forces, like you show me what did you remove. I removed here, for example, this, and you put all the moments. So you put 3. So that's 2 moments, and that's reaction. If you guys remember from the grid has 2 moments and reaction. And the reaction goes up, and the moments is something like this. So same thing here. And reaction, and I had a hinge here. Let's assume cylindrical hinge. The cylindrical hinge has something like this and has a moment. So you have 2, and here's you have 2. Sorry, here's 3, and there was a hinge. Here you have 3, and here you show the 3 internal force. So I have 3, 6, 9, 11, 13, 15, 18, 21. So I have 21 redundants in this problem. So that's what I'm looking for when I look at the redundants, okay? Degrees of freedom is the same thing. You have to draw your structure and then you show me where's the degrees of freedom. Don't remove hinges or don't remove supports. We don't remove supports here. There is a roller here, so I know that there is a degree of freedom this way, and also there's a moment, like rotation, allowed here. Here, I know that there is a degree of freedom, like for example, it is X, Y, and there is a moment from here and moment from here. Here, I know that there is moment, here there is nothing, here there's 3, so I put all the degrees of freedom. Put numbers, and you are done with the degrees of freedom. That's what I'm looking for in the exam, to see. Okay, so that you don't lose points. First, you have also, I saw some of you, they don't write the whole equation. You just like tell me, for example, IS is equal to 3. That's it. What I want to see when I give you points for this problem, I want to see IS is equal to 3M plus R plus RS minus 3 joints plus S. The rule, and then you substitute in the rule and then put the final number. That's the 3 steps, the 3 points. 1, 2, 3. Okay? You put 1, you get 1 point. You put the 3, you get the 3 points. Okay? That's the same thing with IK. You have to put all the IK equation. Okay? Have to put everything. Okay? All right. So does anybody have any comment? Some of you did the whole quiz wrong, but I'm not grading on the final answer. I'm giving some points for the effort. Same thing with homework. Some of you would have wrong answers, but I have the model answer out there, but I give you based on your effort in the homework, okay? All right, does anybody have any questions so far? All right. Okay. Do you guys remember the last thing that we talked about last time? Arches, right? Let's continue on the analysis of arches. So last time we started talking about arches, and we talked specifically about the funicular arches, right? Mm-hmm. So I'm gonna remind you, what does it mean by a funicular arch? Arch that has the bending moment equal to 0. And how we can make an arch funicular?
By
treating it like a cable.
Yeah, so by treating it like an inverted cable, like if the cable is going this way, because cables are always follow the general cable theory, right? Because it's a cable. Once you put the load, it's gonna take a shape. This shape is funicular, because the cable always have the bending moment equal to 0, right? So if the arch is following a general cable theory, that means that the bending moment at any point on this arch is equal to 0. That means that the arch is funicular, okay? And I talked last time about why it's important to have the moment is equal to 0, right? Because we talked, like, if you guys, all of you design reinforced concrete or steel sections, right? All right, so when you design, we don't design for, we don't like say, okay, this is moment, I'm gonna put this. We convert the internal forces to stresses and see what kind of stresses they make on the cross section. Like if I have a reinforced concrete section like this, and it has a compression load that comes from all the loads from other stories that comes on this. So this is gonna make compression. I can resist this compression with just concrete, but we usually put a steel because of the buckling, because of the bending moment, accidental bending moment if it has pure compression, okay? But if this cross section has a normal force and has a bending moment, this bending moment is also converted to axial forces, like it makes tension in this cross section and makes compression in this cross section, okay? So as I told you last time, bending moment is very bad for structures, okay? But it's inevitable. We can't avoid it. So the way to deal with it, we have to resist it by something that can resist tension and something that can resist compression. Concrete is very good in compression. Steel is very good in tension and compression. But we use it here for tension. So we put it where the tension is, and we have concrete all over the place. And also one of the bad things is, you can't put a reinforcement here, like, okay, you can't make a cross section, a bunch of concrete here and a bunch of steel here. That's not a cross section. If there is a steel, you have also to cover it with concrete. And all the concrete that we have here is a waste, because they are all gonna be cracked once the tension happens. But the steel are gonna put them in place, okay? So that's why I'm telling you, bending moment is very bad for engineers, because it's a lot of waste of concrete that we have here. The more that we make this moment is less, the more our cross sections are gonna be less, and the more that we save money. And the more that you save money, the more that you are a better engineer. So that's what we are trying to do. So making a funicular shape arch is gonna make the bending moment less, or make the bending moment 0. Sometimes we can't follow the funicular shape, because I don't wanna like an arch that's very high. Sometimes we just need like a little bit. So the less moment is good. Like sometimes we tolerate 10% of the moment or 20% of the moment. That's okay with me. I'm gonna put less reinforcement. That's fine with me, okay? But I'm telling you what is the perfect shape that is gonna give you 0, but this doesn't mean that you have to do it. You can decide whatever you want, but you know that arches can reduce the bending moment, okay? And pick the shape that is gonna fit for your design and is gonna be acceptable for the architecture. And this is gonna make you save money through saving in reinforcement by reducing the bending moment, okay? So right, so we passed this discussion, but last time when we discussing this funicular shape, we did it on concentrated load. Like we have an arch that has a bunch of concentrated load, and we solved this problem. What if my arch has like a distributed load? What is gonna be the difference? Okay, like I have an arch like this, and I have bin here. This is a hinge, and this is also a hinge, and I have an intermediate hinge here, and I'm telling you that this arch has a load something like this, and this load is W, and here I have these distances are L over 2, and the height of the arch is H. All right, so that's a general arch that we need to solve, or need to develop an equations to solve. But I want to talk a little bit before this about the load distributions. So, just want to make sure that you guys understand the different way to represent loads. Okay, what if I give you a problem that has something like this W, and that's L, and it's W, it's L, and W. Okay, I'm gonna say that this is L dash, and this is L. W, H. All right, so I just wanna teach you, if I give you a problem and I put a bunch of loads, like a load on a specific beam or frame, each one of these is different, okay? So let's see what is the difference. We need to identify what is the resultant of the load and what is the direction of the load for each one. What is the resultant of this load on the beam? WL or WL bar or L dash? L dash. Why? Because that's a horizontally projected load. That means this beam has this load distributed on this lens, not this lens. Okay? So the resultant is W L dash, right? Okay. What is the direction of this load?
Down.
It's going down like this, right? All right. How about this one? What is the resultant of this load? This one is distributed over the whole length of the beam, not the horizontal projection. So it's distributed over L. So that's W, L. What is the direction of this load? It's going down, right? Because I have my hatch is going down. How about this load? That's also WL, but what is the difference? It is going this way. That means that this load, and rarely in our application that we have a load going this way. I mean, unless that you make something that goes this way. All our loads going towards the gravity direction, going down, okay? So that's like kind of example if you have a staircase, like stairs, the stairs load is something like this because you are going up, so the load is going up. So there's different ways that we can calculate the staircase load. We can calculate the whole load and distribute it over the full length of the beam, or we distribute it over the horizontally projected length of the beam. Sometimes I can give you the load W distributed over L, and then I write HB in front of it. That means, I'm teaching you this because sometimes you have a textbook and they have the loads in different ways. So when you see these loads in different ways, you understand what this means, okay? So W and have HB in front of it, that means that this W, however, it shows it's distributed over the whole length of the beam, but I give you the value that is horizontally projected on the beam. So that means that R is equal to W multiplied by L dash, not the whole L. So that's the difference between this one and this one. So this one is the same like this one, okay? Because some textbooks don't like to write the load away from the beam. So they put them that way. And they tell you that's horizontally projected. And also, I believe in SAP 2000, it's always, all the load are horizontally projected, okay? All right, so I have this load. What is the resultant of this load? That's W multiplied by the whole length L, because that's an arch, okay? It's not gonna be easy for me to distribute the load over the length of the arch, so you have to find what is the length of this curve. So that's why that is the best way to represent this load. Okay, we passed this. The next step is to solve this arch. I wanna solve this arch, I wanna find the internal force in this arch. What is the compression that this arch is making? But I'm telling you that this is a funicular shape, or I want to make this arch funicular. to do this, I need to build the geometry of the arch. To build the geometry of the arch, I need to pick an axis. So I'm gonna put my XY axes here, X and Y. And to make this arch funicular, that I want the moment at any arbitrary cross section to be equal to 0. So if I pick any of these cross sections and I get the moment either from the left or from the right, it should give me 0. That's the target. Okay, so let's see how we can do this. But before I do this, let's find the reactions. Before you solve any problems, before you calculate any moments, you need to find what is the value of the reaction. The vertical reactions are very easy. Do you guys know what is the value of it? WL over 2, because the whole resultant is WL and it's symmetric, so this takes WL over 2 and this takes WL over 2. What about the horizontals? I know that the horizontal reaction is going to go this way because the load want to open the arch and the reaction is pushing the other way. Okay, so let's find the horizontal reactions. H. How can I find it? What is the easiest way to find it? Where? You can take the moment here, but the thing is, if you take the moment here, this H is going to be multiplied by arm 0. So you need to take the moment at this intermediate hinge so that the horizontal load can have an arm. So what I'm going to do, let's name these letters like the way that I have it here. A, B, and C. So what I'm going to do, I'm going to take the sum of the moment at C equal to 0 from the right. And I'm going to make the positive this way. So let's see what forces that make moment. I have this reaction, and this load. I have 3 forces. So I have the horizontal reaction multiplied by the height minus WL over 2 multiplied by L over 2 plus W, the resultant of just this piece is WL over 2 multiplied by the arm. Like if I have this, the arm is going to be here, so it's going to be at distance L over 4. Okay, so that's all the moment, and all this should be equal to 0 because the moment here is 0. So this is going to give you that H multiplied by H is going to be equal to WL squared over 8. So the horizontal reaction is going to be WL squared over 8H. Okay, so we got the horizontal reaction. All right, what is the next step? Next step, to make this arch funicular, the moment at any cross section should be equal to 0. So what I'm going to do, I'm going to pick any random section at a distance random x, like let's say this distance is x. I'm going to call this D, right? So this is x and this is D. So the height from here to here, so this is going to be, let's name it, okay, I'm going to name this H capital. And this is going to be H small. Let's follow the same way that I did it. I call it here actually Y, okay, so that you guys don't get confused. Okay, I'm gonna call this X and Y. And let's keep this, because we already have H capital for the horizontal load. So let's make this H, and I'm gonna call this Y. X and Y. All right, so this point at the distance Y and X, all right? I want to get the moment at this cross section. By the way, the moment here is not 0. We want it to be 0, but it's a general moment. So I'm going to get the moment about D. So let's say MD. What is the best way to get this moment? From the left or from the right? Right. Why? Because it's less loads. Well, not that much, but it's like much better. Like it's much less here. Okay, let's see. So if I want to take the moment about this point from the right, what loads that is making moment? WL over 2, H, and also a piece of the distributed load. Okay, so let's find how much moment that the horizontal load is making, and it's positive or negative. Okay, by the way, right now we are dealing with signs. Like, you guys remember what is the sign convention for the moment? The positive sign, if the moment is this way from the left, But right now I'm not focusing on the left, I'm focusing on the right. So the positive moment should be this way. So any load that makes moment this way is gonna be positive, and the opposite direction is gonna be negative. So let's see, who's making positive? I'm gonna make this one, because this one is making positive moment, WL over 2. So WL over 2 is gonna multiply by this distance, which is L over 2 minus X. So I'm gonna have WL over 2 multiplied by L over 2 minus X. Next one is the horizontal load. The horizontal load is negative, multiplied by this distance, which is this whole h minus y. So h minus y. And next one is this piece of w. The piece of w is multiplied by, this is the distance, so I'm gonna have minus w multiplied by the length that is distributed on, which is this distance, which is L over 2 minus x. By the way, I only got the resultant of the w. I need to get the arm of w. So it's gonna be this thing multiplied by L over 2 minus x over 2. Okay? So that's the moment at D. All right? So maybe you go try it at home with yourself and see if this is right or wrong. Okay? There's lots of x's, lots of parameters. Once you expand this and expand this and expand this, MV is going to be equal to WL squared over y. No, WL squared y over 8h minus WX squared over 2. Once you expand these parentheses, once you open these brackets and sum each one together, some are gonna cancel each other, some are can get summed together. So once you do them, you're gonna end up with this. And substitute h with this value. Like remove this h and put WL squared over 8h. Okay? You are gonna end up with this final formula. Okay, that's the general moment at any cross section, right? So I want to make this moment 0. This moment to be 0, so you are gonna say if MD for, let's make it over there. If the arch, let me write it here, F the arch is funicular, MD should be equal to 0. So WL squared y over 8h should be equal to WX squared over 2. So once you do the math, you will find that y, and this 2 is going to be here 4, is going to be 4h over L squared multiplied by x squared. All right, so that's how you make this arch funicular. You put x here 1, substitute with all these parameters and get y. And you do like maybe 5 points or 3 points to build this arch. So we got this equation. All right, so we got y. So what if we want to find out the total axial compression in the arch? Because that's what we are looking for. In the cables, we're looking for the tension in the cable, but the arch doesn't have tension, it has compression, it's different, okay? The cable was like this and all the load goes down and it is pull the cable and make tension in the cable. Right now our arch like this, all the load like this, and all the arch is in compression. And actually that was the objective. We are making arches to convert all the tensions inside the cross section to compression. Okay, so let's find out the total axial compression. Okay, for the total axial compression, it's going to be the same thing. We are going to say that the compression is going to be equal to the horizontal load over cosine theta. Because it's the same thing. If you have your arch like this, right? And actually, that's the compression in the arch. Like, let's say that the compression is going this way. So the compression has two components. Has a component like this, it's the horizontal component H, and has a vertical component like this, okay? And you have here H, and you have here the reaction. And this is theta, and this is the compression that we are looking for. All right, so H here is equal to H here from sum of the horizontal forces. You will find that the horizontal here, as soon as the arch doesn't have any external horizontal loads, so this H is equal to this H. So H is equal to the compression in the arch multiplied by cosine theta at this point. So if you find the compression, it's gonna be H over cosine theta. So it is the same thing. By the way, I write it here T, but it should be C, compression, but whatever, it's a symbol, okay? All right, so I have C, I don't have C, that's what I'm looking for. I have H, because I already got H here, but I don't have cosine theta. How can I get cosine theta? You guys tell me. I wanna get theta here, at any section. Given that this is the equation of the arch, what should I do?
Differentiation of
I differentiate this equation, dy d theta, dy dx. What is dy dx? It is tan theta, right? So dy dx, when I differentiate this, is gonna be 8h over L squared multiplied by x, right? So right now I got tan theta. And actually from the geometry, I can make a triangle. That's what we do. Any triangle, that's how I get cosine out of tan from the geometry. So I will assume that this is theta, and I know that tan theta, if I have this is 1, and this is 8h x over L squared, tan theta is gonna be this over 1, which I will assume that there is a 1 here. So that is the opposite, and that is the adjacent. So it's the opposite over the adjacent, which is this one. And I'm gonna call this R, okay? So if I wanna find a cosine theta out of a tan theta, that's what I do by geometry. I put a triangle, I assume theta, I assume this value is over 1. So I put this here in the opposite, I put 1 in the adjacent, and I know for sure that tan theta is this over this. So this triangle represents this formula. So I can use the Pythagorean theory, and I say that R is the square root of 1 squared plus 8h over L squared multiplied by x all squared, right? This is R. So if I want to find cosine theta, it's gonna be 1 over R, right? So it's gonna be 1 over this value. All squared. All right, I got cosine theta. Let's continue. So right now I can say that the compression, C, is equal to the horizontal over cosine theta. So it's gonna be the horizontal over, by the way, it's 1 over, so I have another 1 over root 1 plus 8h over L squared multiplied by x squared, all squared. No, sorry, it's x. All right, so that's what I have. So this root is gonna go up, and this means that the h is gonna be equal, the compression is gonna be equal to h multiplied by 1 plus 8h over L squared multiplied by x all squared. So the conclusion is that the compression is gonna be 1 plus 8h over L squared multiplied by x all squared. And that's what I'm looking for. So right now I have the general equation of the axial compression inside an arch, okay? And I have H already from here. Does anybody have any questions so far? Is this geometry hard, this part? Okay, all right, so we are done with this part. So let's apply this on a real problem. Let's put real number and see how this equation is gonna fit, and do a little bit of structure analysis. All right, so I have an arch like this, same arch. And I'm gonna put load W. And I have a real distance here. This load is 5 kips. Kips means kilopound per feet. And I have here 70 foot and 70 foot. And I have the height here is 42 foot. That's the height edge. Okay? So that's everything that you need. And I'm saying establish the funicular shape. And when I said that, I give you 3 points to help you. Like if this is X and Y axis, okay, I give you a point here, and a point here. I told you that this is X1, this is X2, and this is X3. And X1 is equal to 17.5 foot, X2 is equal to 35 foot, and X3 is 52.5 foot. So that's the first thing that I asked you for. And the second thing I asked you for, it's a design question. Determine the minimum cross section. The minimum cross section at X1, X2, X3. And since it's a design question, I ask you to determine cross section, so I should give you the allowable stresses, because that's what we do. If we design a concrete, we know the allowable stresses in concrete or steel. So I give you that sigma allowable in the cross section is 2,000 pound per square inch. Okay, so that's a problem. Okay, to establish the funicular shape, we spent like half an hour to find this. Okay, so right now we have y as a function of x squared, because this problem is this problem. So what I'm gonna do, I'm just gonna substitute in the function of this arch, which is y equal to 4h over L squared multiplied by x squared. So y1 at x1, which is gonna be this one. So if I substitute, I have h is 42, so I'm gonna say 4 multiplied by 42 over L squared. L squared is 140 squared, and x is this x1. It's 17.5 all squared. So once you substitute, you will find that this is 2.6 foot. Same thing, I'm gonna do it with y3, y2. It's gonna be 4 multiplied by, h is the same, 42 over 140 squared multiplied by x2. x2 is 35, so I'm gonna put 35 squared. And this is gonna be 10.5 foot. And y3, 4 multiplied by 42 over 140 squared multiplied by 52.5 squared. So this is gonna give you 32.6 foot. And that makes sense, because here x is small, getting bigger and much bigger, and I got all y1, y2. Right now, I established the funicular shape of an arch by getting the xy coordinate of 3 points in the middle. So you can just locate these points, connect them, you built the arch. I got number 1. Number 2, it's a design question. I'm asking you to find a cross section. To find a cross section, what do I need? Knowing that sigma. Okay, what is sigma equal to? What is the stress? Stress is the force over the area of the cross section. So the force is gonna be the compression over the cross section area, right? Okay, so I know this, right? And there is a way that I can know the compression because we just drove the equation, right? So if you know these two, you can find the cross section area. The cross section area is gonna be C over sigma. But you know the cross section area. Okay, yeah, the minimum cross section. Okay, I'm gonna show you how we can find the dimension of the cross section. Okay, but right now let's find the cross section area. By finding the cross section area, we need to find what is the compression in each cross section. So let's find the compression in cross section number 1 at x equal 17.5 foot. It's gonna be the horizontal. We need to find the horizontal first. Let's find it out. And that's easy. I have the horizontal force equation. You guys can tell me what this equation is. Can you look it on the board? It's all over there. W L squared over 8H, right? Okay, I have W is 5, L squared is 140, all the square over 8H, H is 42. So once you solve this, it's gonna give you 291.7 kips. All right, right now I'm ready to substitute here because I got H. So I know that C is equal to H multiplied by the square root of 1 plus 8H over L squared multiplied by X all squared. So I can get C1. C1 is gonna have X1 here. That's the only variable in this equation. So it's gonna be 291.7 multiplied by the square root 1, 8H, which is 42, over L squared, which is 140 squared, multiplied by X. By the way, make sure that everything is in parentheses and this all squared. Don't get the X out. And X is not a square. X is to the power 1. So X is 17.5. And all this is squared and all of them is under the root. So once you find this out, it's going to be 304.5 kips. Same thing, I'm going to go to a C2, but I'm going to substitute right away. 291 square root of 1 plus 8 multiplied by 42 over 140 squared. And all this is multiplied by 35, and all this is squared. Once you substitute, you will find out that this is 170.1, sorry, it's 340. Let me ask you, the way that I go down, the compression force increase or decrease?
Increase down.
Why?
Because
Because of the slope, right? That's why, like, when I put a number here that is less than this number, so there's something wrong. I was about to put 170. I was like, oh, this is 304, there's something wrong. So I looked again, so I saw that I picked another number. So this one is 340.2, and that's what you should do in the exam. When you solve the exam, try to check your number. Does it make sense or not? The seed is getting bigger. Why the compression is not getting bigger? Okay, so 340.2 kips. And same thing, once you get C3, you are substituting with everything. I put here 0.7 and the square root. And once you get this, it's gonna be 392. It's getting bigger, which means that I'm in the right way, 0.4 kips. All right, did I get the cross section? No, I just get the compression, but I'm so close. I have the compression, I have the segment. Right now I can get the cross section for each one. So here, what I can do, I can say that A1 is gonna be equal to the compression 1 over the sigma. So compression is 304.5 over 2000. But what's wrong here? The kips, it's a kilopound, and this is pound per square inch, so I have to multiply this by 10 to the power of 3. Pay attention to the units, okay? So this is gonna be 152.3 inch square. And this is the same thing A2 is gonna be C2 over sigma, so it's gonna be 340.2 over 2000, and this is multiplied by 10 to the power 3, so 170.1 inches squared. And A3, after you substitute, is gonna be 196.2 inch squared. All right, so I got the minimum cross section. If you wanna imagine how this is gonna look like, we are gonna assume that this arch has one dimension is constant and one dimension is variable. Like, we are gonna assume that this arch is gonna, for example, look let me make like a 3D of this arch. It's gonna be maybe something. Something like this. Alright, and then let's hinge. Actually, let's make it as a real life. Usually, let's say it's on a footing, something like this, and a footing, something like this. And the way to make this hinge can be like something like this. And something like this. Okay. And to make a hinge here, like if you have a reinforcement, it's gonna be like something like this. And here's the reinforcement is gonna be something like this. That's how you make this is like a hinge. So I'm gonna assume that the cross section, one dimension of this arch is something constant like this, like have the same widths. Okay. Something like this, okay? So what is it changing is the depth of this arch. Like the depth here, the depth here is one value, is another value. Sorry, the depth, this one. Here and here, okay? Two different V depths. To do this, I'm gonna assume that B is 10 inches. 10 inches is like 25 centimeters, which is the regular depth of concrete beam. So I'm gonna assume that the width of the cross section is equal to 10 inches. Let's find the other dimension, because this cross section, if you take it out, it's gonna be something like this. And I assume that this is 10 inches. I wanna find out what is the other cross section. So we will find that, let's assume that the width is B equal to 10 inch. That's the width. And let's find the depth of the beam. The depth of the beam, once you divide the area over B, which is 152.3 over 10. So this is gonna give you 15.2 inch. Same thing here, you will find that the depth is 17 inch. And here you will find that this is 19.6 inch. And right now we designed an arch. We found what is the compression inside the arch. We find what is the cross-section area. And then we find out what is the dimension of the arch, assuming that the width is 10, so we find out what is the other dimension, okay? Does any of you have any questions so far? All right, definitely we'll put reinforcement in arches. Like any reinforced concrete structure, we put reinforcement even if it doesn't need, for shrinkage, for many things, like just for your information. Like we're not gonna make it pure concrete. Okay. Yeah.
I do have a question. So for the equations that we have of the y and everything are x, so a reference point is the uppermost point of the arc, right?
Exactly, this one. Yeah, but you can put your coordinates here, but
It's gonna
since
be-
the start of the problem, you deal with everything started from the x here.
Got it.
Like if you put it here, everything, this cross section is gonna be with respect to the x here. And you're gonna get different equation that is valid for what, for your assumption.
Got it.
Both of them are gonna be the same. All right, so the next thing, actually right now we finished like the part that is gonna be included in the midterm next week. As I told you, we're gonna have one question on the determinant and indeterminate, one question on arches and cables. Might be an arch, might be a cable, so you need to study both. We're gonna have one on the deformation. We're gonna continue the deformation topic on beams and frames after the after the midterm, like maybe after 2 weeks or something. But I wanna touch base on analysis using SAP 2000. So the thing is, to do the project, we are gonna do the project for this class on ETAPS. But ETAPS and SAP 2000 are very close, so I'm gonna introduce some concepts that for ETAPS, or we're gonna introduce the analysis of structures using software using SAP 2000. And once we finish SAP 2000, maybe, I don't know, like after 3 weeks from now, we are gonna head to ETAPS, how we model buildings on ETAPS, so that we can know how to do the project. The project is gonna be like a seismic analysis project, and it's gonna be 60-story building. Definitely, we are not gonna make like a difficult example. Like I'm not gonna give you a project that like needs like 6 or 10 engineers to work on. It's gonna be a very, very simple building. The thing is, we just wanna understand how the lateral load resisting systems in tall buildings work. That is the main concept of this. That's what the main goal of this project, to understand this. So the goals of this course is to know how to do structure analysis, knowing that you have the basics, but I'm taking you to the advanced level, and how to take the advanced level to applications. So usually application is taught in concrete classes, but I'm not gonna design the building, I'm not gonna design the beams or slab. All what we want to know, what is the internal forces in the structure, how applying different mitigation or different design strategy or different analysis strategy is gonna help our structure to perform more, and how we can feel the structures as a structure engineer, okay? So I'm gonna start with SAP 2000 verse to like lay out how to do analysis for software, and once we have our hands on the software and do a bunch of examples and homeworks, we take it to the next level on ETAPS, and then we take it to the class project. So the class project is gonna be groups. I understand we have like 13 students in this class, so we might have 3 groups. Each group is like around 4, maybe 4 groups, each group around 3 or 4. I believe 3 is a good number, so that's one thing that I need to mention. Yeah, for the software. So right now in the process of purchasing the software for our class, somehow I find out that EIC doesn't have the software on their list. So I submitted a ticket, and we are gonna purchase the software, but until we purchase the software, all what I want you to do, you go to Google and search SAP 2000 free trial. So once you do the free trial, it's gonna give you an application or a form to fill. And once you fill this form, it's gonna give you 1 month free trial on SAP 2000. That's just gonna help us to use this SAP 2000 until this 1 month. And I believe after 1 month, we're not gonna need SAP 2000 because we are gonna head to ETAPS. And we are gonna do the same thing with ETAPS if it's delayed. Like we're gonna get the free trial and work on it, okay? So that's what I want you to do for now. Go to Google, SAP 2000 free trial, fill the application, and then download the software and install it. But not right now. I mean, like when we start, so that we can use the whole month. I don't want you like to download it now and wait like 10 days. Once you hit the first homework, download it, so you don't have it, just in case if the license got delayed from the EIC, so that we have a backup. All right, so before I start the The SAP 2000 part, I need you to understand a few things. I'm gonna talk about them in this 10 minutes. All right. So, you guys all working on software, right? Like, have you guys worked on SAP 2000 before?
No.
Okay, how many of you didn't do any SAP 2000 analysis before?
Haven't done.
Haven't done any. Okay, how many of you haven't done any structure analysis software other than SAP 2000, like ETABS, any structure analysis software? Did any of you, all of you worked on a structure analysis softwares before, ETABS, RAM? Okay, so the concept in all the structure analysis software is the same. They are mostly the same element that is being used to modeling structures. So either SAP 2000, either ETABS, Robot, all the structure analysis software, they have almost the same elements. So the elements to model the structures, we have mainly 4 elements that we use to model a structure. We have frame element, we have plate element, we have membrane, and we have shell. Let's talk about them first. So in SAP 2000, to model a beam, a frame, a truss, an arch, any linear structure, we use something that's called a frame element. Okay? Any linear structure, a frame, a beam, an arch, a grid, everything is gonna be with frame. However, to model 2D element like the slab, you will tell me, oh, the slab is not 2D, it's a 3D because it has thickness, but the thickness is very, very small compared to the other 2 dimensions. So we usually simplify it by modeling as a 2D element. If the thickness is very, very big, neglecting the thickness is gonna make your analysis not accurate. Like if you have a raft foundation and this raft foundation is 3 meter height, that's modeling it as a 2D is not a good because the depth is huge. Okay, so we model solid element, but we're not getting into solid element. Let's focus on 2D element, like slabs. So, what other 2D elements that we have that are different from the slabs? The shear walls. Shear walls is an element that is like a big column, a very, very long column, that we can't neglect the other element. Like the column, we do a 2D, but the thing is, because it's like, the column is like going from first story to the last story, and it has 2 dimensions. So what we do, we make a frame element for the entire column. But if there is a shear wall, there's 1 dimension that is huge, or 2 dimensions. So we model it as a 2D element. By the way, the more that you increase your resolution, like the more that you model the column, like let's assume, oh, can I model the column as a 2D? Yes, you can. Like you can make the column as a 2D element, like as a shell element, and that's fine. But it's gonna make your analysis take much longer time, okay? Can you model the column as a solid? Yes, you can model the whole building as a solid, but it's gonna take a huge time to run. So we make some simplification or assumptions that make the analysis much faster and we don't compromise the accuracy. Do you guys understand what I mean? So that's why we model like columns, beams as a frame, but if you model them as a shell, that's fine. I had a class back in the days that we were trying to model the column as a beam, as a shell, as a frame, many things, and try to compare with the analysis. It wasn't that much, okay? And you can do it yourself. Okay, so we have these 3. Mainly that we use for structure analysis is the frame and the shell. So what is the plate and membrane? Okay, so I told you about the frame, and let me actually finish the frame. The frame is usually a line, something like this, has an end point and a starting point, and has 6 degrees of freedom at each point. What are these 6 degrees of freedom? It has a translation about an X and Y and Z, and it allows the rotation about each one of these axes. And there is also a 6, and it allows rotation about the 6. So what is the total number of degrees of freedom, of the degrees of freedom at this frame? You have 6 here and 6 here. 12, right? it's like something like this. This point can move X, can move Y, can move Z, and can rotate about X, rotate about Y, rotate about Z. So it has a freedom to go in the space. Same thing, this point. 6 degrees of freedom here and 6 degrees of freedom here, that makes it 212. All right, about the plate is like the floor that we are standing on. This floor in the middle, let's assume in the middle, it can rotate this way. I mean, like bending this way, and can rotate this way, because this, when it goes down, this slab is bending this way and bending this way, but doesn't allow torsion. Like this slab doesn't go this way, shouldn't go this way. So it doesn't allow rotation in this direction, but it allows deformation goes down. It shouldn't goes X and shouldn't goes Y. Okay, so this point can go down, can rotate this way. 3 degrees of freedom at each single point. So plates is something like this. Actually, membrane and shell. So plates has two moments about X and Y, moment, and has one vertical. Same thing here, 2 moments and 1 vertical, 2 moments and 1 vertical, 2 moments and 1 vertical. 3, 3, 3, 3, 4 threes. How many the total number of degrees of freedom? 12. And here is 12 as well. Membrane is the opposite of this. Membrane is like something like shear walls. Shear walls is an element like this, takes the load this way. The slab takes the load this way, right? When we sit on the slab, it takes the load this way. But shear walls is something like this. It resists the lateral loads that are coming from the earthquake. If you have building and you have a shear wall, which is a long column or a wide column, and all the loads want to take the building this way, so the slab is taking the moment this way. So there is a moment in plane, and the moment in plane is torsion, right? Something like this. So there is a moment this way, okay? But it shouldn't bend this way or bend this way. There might be buckling, but it's very, very minimal compared to the other bending moment that we have, okay? So there's a moment this way, and each point can go X and Y. It's not like the slab, it's something like this, okay? So the membrane is the opposite. It's gonna be X and Y translation and moment about the other axis. Same thing here, and moment here, and moment here. So also the degrees of freedom is 12. How about shell? Shell is the combination between plate and membrane. So you get rid of the headache. Is that a membrane or is that a plate? Like, okay, I have an element, like, okay, I have the shear wall, but I'm afraid that the shear wall is gonna have a buckling, and the buckling is gonna make out of plane bending moment. So it's better to model it as a shell, because it's gonna have a combination between the bending moment and the torsion. Okay, so the shell is taking all of these. Every point on the shell has 3 translation and 3 bending moment. Like you take this one moment with these 2 moment is gonna be 3, and these 2 translation with this one translation is gonna be 12. So each point is gonna have 12 degrees of freedom. 3 translations, 3 rotation. Okay, so the total number of degrees of freedom is 24. That's all the element that we used to model. So when I'm gonna model structure on software analysis, I'm gonna use plate, I will never use membrane. I will use frames to model beams and columns. I'm gonna use shells to model slabs and shear walls. That's what I'm gonna use, but I have to tell you what is plate, what is plate, and what is membrane. Okay? All right. Also, let me introduce something with you about the units. Unit conversion. Okay, so the Pascal is a Newton over meter square. And 1 megapascal is 1 Newton per millimeter square, and this is equal to 145 pound per square inch, PSI, okay? That is a pressure unit, because we are gonna define units. That's the first thing we are going to do on software. We define the units that we are gonna use. So we have, like, for example, we say, like, what is, if we have concrete 30, that's a type of concrete, and that's mean that the compressive strength of this concrete is 30 megapascal, which means it's a 30 Newton per millimeter square. Okay, so if you want to convert this to ton per meter square, do you guys know how? I need to convert the Newton to ton and the millimeter square to meter square. So if you want to do this, this is the 30. The Newton is 1 over 10 kilogram, right? And the ton is 1,000 kilograms. So I have 10 over 10 multiplied by 1,000 here. So I converted the Newton to ton. And if I want to convert the millimeter, 1 millimeter, that's a 30 over 1, to meter square, the millimeter is 10 to the power negative 3, but if it's a square, it's going to be 10 to the power negative 6. So once you do this, you will find out that this is 3,058 ton per meter squared. So you need to be very good in converting units. Here I converted Newton millimeter square to ton meter square. 30, converted the Newton to ton, the millimeter to meter square. All right, also some stuff that you need to know. The Young's modulus of the concrete is 4,700 root FC. This is if you have the units in megapascal, or it's 557,000 root FC if this is in PSI, pound per square inch, like if you have FC is in pound per square inch. The Young's modulus of the concrete is 0.2. This is the epsilon, which is the longitudinal strain over the longitude, like the two strains. Like if you have this, there's a strain this way and there's a strain in the other way, the ratio between them. And the gamma of the concrete is 2.4 ton per meter cube. That's the density of the concrete. So this is things that you need to know about concrete. I'm assuming that you know all this for materials. And steel, the Young's modulus of the steel is 200,000 megapascal. Definitely depends on the concrete type, but I'm saying that this is the units that I'm gonna use in SAP 2000, but definitely you might have high strength concrete, different type of steel. So this is megapascal, and the epsilon is gonna be equal to 0.3, and the gamma of this steel is 7.85 ton per meter cube. That is the things that I want you to need to know about the concrete and the steel, because we defined this before we start our problems for concrete and steels, and this is some unit conversion that you need to be familiar with. All right, so I hope that you guys will study well. You will be allowed in the exam to have one sheet to put the rules, to put whatever you want, and get in the exam and solve your exam, okay? If you have any questions, just message me, and then we'll take it from there. I will having office hours, so if you want to come and ask questions, I will be there.